All right, so I'm going to start you off with what looks like a really innocent equation here. Solve for x. 2 to the blank power equals 27. That doesn't look too hard, does it? Let's actually start. Let's start with like a little guess and check, okay? So if I do 2 to the first, 2 to the second, that'd be 2 times 2. 2 to the third, that'd be 2 times 2 times 2. 2 to the fourth. I'm going to actually write that one down because that's getting close. So 2 to the fourth, 2 times 2 times 2 times 2, it gives me 16. 2 to the fifth gives me 32. You can see here, I can start to narrow this down. The answer's got to be some decimal between 4 and 5. Okay? Now, so pretty quickly, we can really kind of narrow this down. It's going to be some decimal between 4 and 5. But after that, it starts to get tricky, okay? It's almost this wild goose chase. I'm going to try like 2.45, too small. 2.46, too small. 2.47. I'm sorry, 2 to the 4.7, 2 to the 4.8. Okay, 2 to the 4.8 is too big. 2 to the 4.75, we're getting very close. 2 to the 4.78, a little bit too high. All right, what happens is you start kind of going down this wild goose chase here. Oh, that's a little bit too small. Okay, I'm getting really close, but it's very hard to get this perfectly because it's going to be like an irrational number, okay? So I can make this estimation. It's going to be around, okay, x is approximately 4.75, we'll say 55, but it's not quite perfect, okay? With guess and check, I'm going to be able to get an estimated answer, but it's a pain in the butt to keep typing all this in, and it never comes out quite perfectly. So how can we solve this using what's called the common log? Here we go. There's a way to solve an equation where the x is an exponent, and you do it using logarithms. Okay, what we're going to do first is I'm going to take the log of both sides of this equation. Okay. Now, in your last lesson, you learned what's called the power rule of logs. And it looks like this. What happens is when you have the log of a number to the x power, that's the same as x times the log of that number. Okay? Here we have log of 2 to the x power. Thanks to the power rule, this can be rewritten as x times the log of 2. And then if I want to solve for x, I'm just going to divide both sides by the log of 2. Now, technically, this works with log of any base. You could technically use any base here. You could do a base 2, a base 3, a base 4, whatever. But since our calculators generally do a log base 10, we're just going to use, that's called the common log, is log base 10. We're just going to use common log because this is going to be very easy to solve in our calculator. To get this answer in our calculator, all we have to do is log base 10 of 27, this is called the common log of 27, divided by the common log of 2. Okay, and here we get this answer without having to guess and check. And this is an irrational number, by the way. But here we get an accuracy of 9 decimal places without having to do any guess and check. That would be a pain to find all of that by guess and check. Now, I will say, I'm going to have you on your assignments just round everything to the nearest thousandth, so to 3 decimal places. But here we can find that answer without doing any guess and check. It ends up being the log of 27 divided by the log of 2. Now, once you get the hang of this, you're going to find there's kind of shortcuts. Okay, so let's do one of these together. So the long way to do this is we say, all right, we take the log of both sides. And then because of the power rule of exponents, this can be rewritten as x times the log of 3. And so to solve for x, I take the log of 35 divided by the log of 3. That's kind of the long way to write out all the steps. But once you get practice, once you get the hang of this, you're going to find a really quick way. This is called a simple exponential function. Equation. When your equations are very simple, you have something to the x power equal to a number. Here's a shortcut. You're just going to learn the shortcut. This is just going to be the log of 30 divided by the log of 5. Right? And this is going to be the log of 7,000 divided by the log of 10. You take the log of the number opposite of the x divided by the log of the base number with the x. All right, so with that in mind, go ahead and find the answers to these 5 questions. Write them down, round to the nearest thousandth. Go ahead and hit pause and try that out. And all right, I'm ready to reveal the answers. Here you go. If you want to check your work, here are your answers, all rounded to the nearest thousandth to 3 decimal places. So this is how we solve a simple exponential equation. All right, let's put it into practice. So these examples, this is going to be a lot more of what your assignment is going to look like. All right, here we go. So here's example number 2. Carton City has a population of 85,000. It grows by 2,550 people a year. How many years will it take it to reach 100,000 people? Well, guess what? We're not going to use log at all to solve this problem because this is good old-fashioned linear growth. Okay, this is a linear growth problem. But the difference is here, we have our starting value. The population starts at 85,000. We have our slope. It grows 2,550 a year. But then here, we don't have the time. We do not have the x value, how much time it takes. We're actually trying to find how many years. We're going to have to solve for x. What we're given is the final answer, the final value. So plugging these into our linear growth formula, we have the final value equal to this slope times an unknown number of years, x. We don't know how many years it's growing by this much. And a starting value, b, of 85,000. We need to solve for time. How many years does it take? How many years will it take to grow from 85,000 to 100,000 by growing at this rate? Solve for x. Well, this is just a plain old x. This x is not the power of x. It's just a plain old x. We can easily solve this in 2 steps. Okay, you learned how to do this back in Unit 1, solving for a linear equation. We're going to subtract the 85,000 from both sides. And then we're going to divide by 2550 both sides. Just simple algebra here, basic Algebra 1 type stuff. It comes out to the nearest thousandth to 5.882 years. 5.822 years. We rounded, so I'll put approximately equal to x. Okay, but this is very basic. The x is a normal x. You don't have to do anything fancy. Subtract 85,000 from both sides. Divide by your coefficient. Boom, there's your answer. All right, now you know it's not going to stay that simple. Let's compare that now to example 3. Larson City has a population of 85,000. It grows by 3% a year. Man, I see that percentage right there. I know right off the bat this is going to be exponential, because it's growing by a percentage every year. How many years will it take Larson City to reach 100,000 people? Well, here's our starting population, 85,000. And here's our final answer. Like, here's the final result. The final result is that we want it to grow to 100,000. Here's our rate. All right, so let's remember our exponential formula. Here's the exponential formula we've been using this entire chapter. Let's start plugging these numbers in. So I know what I want the final result to be, 100,000. I know what it begins at. It begins at 85,000. And then my R value is 3%. I'm going to write that as 0.03. But I do not know the X. Now I want you to notice this right off the bat. This X is not a normal X. Notice this is an X power. And so the same rules that we applied over here to solve for x, those don't work anymore. As a matter of fact, it's impossible to solve for an x that's written as a power. Okay, so what we need to do, first we need to simplify this. We're going to divide both sides by this 85,000. Okay, so 100,000 divided by 85,000. Now, I know this comes out kind of messy, but I'm gonna write a lot of decimal places for this, okay? If I want my final answer to be accurate to 3 decimal places, then I should go probably at least 5 decimal places in this particular case. Okay, but once I do that move, once I divide this 85,000 away from both sides, look what I have here. This is just a basic, simple exponential equation, just like what we were doing up here. Okay, you have a number to the x power equal to another number. We know how to solve this. We know we're going to take the log of 1.7647 and divide it by the log of 1.03. Now, if you want to see everything worked out, okay, because of that, because of your power rule, right? Because of the power rule, when you take the log of this side, the x becomes a normal x now. It's no longer a power of x. It's now a normal x because you took the log of that side. And so our final answer is the log of this decimal divided by the log of 1.03. Okay, and here's even a little trick you can do. If you don't want to type this long decimal again, and if you want to get a more accurate answer, watch what we can do here. We can take, I already have this answer in my calculator. I'm going to hit log of the previous answer. I hit second negative sign to get the previous answer. So the log of this previous answer, this long decimal that I don't feel like typing in again and that I want to keep its accuracy, divided by the log of 1.03, it's going to take approximately 5.498 years. Okay, after roughly 5.5 years, right around 5.5 years, this population of 85,000 will expand all the way up to a population of 100,000. Okay, so that's all I have for you for this lesson. On your assignment, use this example number 2. Use this anytime you have a linear growth problem and you're trying to solve for the number of years it takes to grow from this number to this number. Use this example to help you with any linear problems that you have on your assignment. And then over here, if it's exponential, if it's growing by a percentage, use this example to help you with any exponential problems, growth problems that you have on your assignment when you're trying to find the number of years it takes to grow from here to here. All right, best of luck to you. Take care.